This tutorial will show how to use CSiBridge to model staged construction of a cable-stayed bridge using the Construction Scheduler feature. It will have two spans, each 100 meters in length, with a single steel pylon 60 meters tall. The deck will be an ashtray type concrete box section approximately 8 meters wide and will be constructed in 10 stages. The model will be created using bridge components from the Bridge tab and structural objects from the Advanced tab. We start the process by going to the orb and clicking the New Model command. The units will be kilonewton meters. We will construct the model without the use of a template, so we click on the blank button. Next, we will define a layout line. We will set the origin at the pylon location, so the coordinate for the initial station will be at -100 meters along the x direction. The end station data will have a length of 200 meters. We will work in only one window, so close the second window. Next, go to the Components tab and set the Type to Frame properties. Here, we will add pipe sections to define a non-prismatic pylon. Make sure that the frame section property type is set to steel and click the Pipe button. We will start with the bottom section. And enter 1.2 meters for the diameter and 0.05 for the thickness. We will add another pipe section to model the pylon at the top. Here it has a diameter of 0.6 meters and again a thickness of 0.05. Next, we will take the two previously defined sections and create a non-prismatic section. Select Other for the frame section property type and click the non-prismatic button. We will call this section Pylon and we'll use the top section as the start section and the bottom section as the end. The moment of inertias will be varied over the entire length in a cubic variation. Next, we switch to a XZ view at y equals 0. Because the pylon and cables are not components of the bridge object model, we will need to utilize a number of the features found on the Advanced tab. Switching to this tab, we will draw the pylon object. Make sure that pylon is set for the section. We draw the pylon by starting at the top and drawing to the bottom to match our member definition. We draw it close to the midspan, but it does not have to be exact. We will adjust the endpoints to correct the location and height. Right-click on the top of the pylon and set the location by double-clicking. We will set the top at 0, 0, and 50. This places the pylon at mid-span with a height of 50 meters above the deck. Right-click on the bottom of the pylon and set the location to 0, 0, and -10. Next, we will draw joints to model the saddle locations for the cables. The first joint will be 4 meters below the top of the pylon. By clicking on the top of the pylon with the offset set to -4 meters, a joint is added. We leave the Draw command and select the joint just drawn by clicking on it. And then go to the Edit panel and select the Replicate command. Here, we will add additional joints for the saddles at 2-meter intervals below the selected joint. This gives us a total of 9 cable to pylon connections. Returning to the Components tab, we will modify the concrete material property to include time-dependent properties. Make sure that 4000 psi is selected, which is our concrete material, and click the Modify button. Check the Switch to Advanced Property display box, and then the Modify Show Material Properties button. Lastly, click the Time-Dependent Properties button. And in this model, we will include both creep and shrinkage effects. We will set the shrinkage start age to be 3 days, and we'll use the full integration creep analysis type. Next, we will define the concrete box girder to be used for the deck. In the Superstructure panel, select the Deck Sections item, and then the New button. For simplicity, in this tutorial, we will use the Eshto PCI box. In practice, some other custom shape would probably be better suited for a cable-stayed bridge. Verify that the material is 4000 psi concrete, and note that the total width is 8.4 meters. We will leave all other values at their default settings. Next, we switch to the Bridge tab, where we will assemble the bridge components into the bridge object. Click on the New button to start the definition of our bridge object. The bridge object will be aligned to the layout line with a length of 200 meters. We can assign and review the components of the bridge object here, or through the buttons on the bridge objects panel, which is what we will do. Click the Spans button, and note that the deck section has been assigned to the bridge object. Click the Span Items button, and then the User Points command. This is where we can control the location of the cable connections to the deck. We wish to divide the deck up into 10-meter segments for the stays. Points have now been located every 10 meters along the entire 200-meter long bridge. Although we have not completed the model, we will perform an intermediate update of the bridge object. We can use either a spine model or an area model. We will use a spine model with the maximum segment length set to 10 meters. We will update the model again when complete. One last bridge component we should check is the supports, namely the abutments. And we see that abutments have been assigned to each end of the bridge. We will modify the bearings such that the translation along the layout or X direction will be free. We will now switch to an XY plan view at Z equal to 0, which is the elevation of the deck. Next, we will define rigid link structural objects that span from the deck center line to the deck edge where the cables connect. On the Components tab, select the link properties type and click on the New button. The Fix All button is used to restrict any relative deformation. Before we draw the links, we will window in for a better view. Returning to the Advanced tab, which is where we add the structural objects, we click on the Draw Two-Joint Link button. Make sure that the rigid link is shown in the property box. And click on the first joint to the right of the origin. Select Vertical from the Drawing Control box and click to draw one link. Right-click the mouse to stop drawing, and right-click again on the end of the link and then double-click to set the location to 10, 4.2, and 0. Repeat the process for the rigid link on the other side of the deck. Leave the draw mode and select the two rigid links just drawn. And go to the Replicate command. Here we will add links at 10 meters on center for the right span. Switching to a 3D view, we see the added links. Isolating our view on the right side of the bridge, we will next define the cable structural objects. Go to the Components tab, and we will select Cable Properties, and then add a new section. We will define the properties by using a diameter of 0.04 meters. Next, we will draw the cables. Make sure that the line object type and section are set to cable. Draw the cable from the lowest saddle point to the link at the end of the first bridge segment. The cable geometry form will automatically open. Verify that the number of segments is set to 1, which is typically all we need due to the fact that catenary effects are automatically included in the cable. And make sure that the cable type is set to undeformed, as we want the cables to be taut. Repeat the process for the next cable, going up one saddle point and out one bridge segment. Continue this drawing until cables have been added all the way out. Select all the cables using the Select Properties Cable Properties command. And then go to the Replicate command. We will use the Mirror tab and mirror the cables about the plane parallel to X to create the cables on the other side of the deck. Now again, use the Select Properties command, but this time select the cables as well as the rigid links. Again, click on the Replicate command and then the Mirror tab. But this time click on the mirror about plane parallel to Y. This will replicate the cables and links on the left side span. To enhance the view, we will select the Extrude View option. And display the model in full 3D. Next, we will zoom into the base of the pylon so that we may assign support restraints. For the pylon, we will fix the base to restrict all translation and rotation. We will turn off the extruded view so that it will be easier to select objects. Next, we will assign components and objects to the groups that will be needed to define the staged construction. Start by switching the view to a XZ plan and turning on the perspective view. Returning to the Bridge tab, we will first assign components that are part of the bridge object. We will create a total of 20 groups labeled sequentially as such. Clicking the Groups button, we click the Add New Groups followed by the Add New Group. We will name the first group Deck 1, and we'll repeat this process to create a total of 20 groups. Next, we will assign the deck segments to these groups. The deck for Group 1 spans from Station 90 to Station 100. Make sure that the deck item is checked. We will repeat this process for all of the other groups until we reach Deck 19. For the group Deck 19, because it is at the end, we will check all to make sure that the abutment bearings are included. The same is true for Deck 20 at the other end of the bridge. With the bridge components assigned to the groups, we will again update the model. Next, we will add the structural items to our groups that are not part of the bridge object. These include the cables, the pylon, and the links, although in this model we can skip the links as they are completely rigid. We start with the cables, and because they are structural objects, we will need to do the group assignment using the Advanced tab. Start by selecting the two cables just to the left of the pylon. On the Assign panel, click on the More button, and then the Assign to Group command. These two cables will be assigned to the Deck 1 group. Make sure the Add to Group option is selected. Next, select the two cables just to the right. These will be added to the Deck 2 group. Repeat this process until all of the cables have been added to their adjacent deck groups. Lastly, select the pylon and go to the Assign to Group command and add a new group called Pylon. The next step is to schedule the stages of construction using the construction scheduler found on the Analysis tab. Items input here will be converted into stages and cases under Load Cases. Stages may involve changes in the structure, application of load, and/or elapsed time, during which creep, shrinkage, and material aging may occur. First click the Add New Schedule button, and then OK for the default schedule name. We start by entering Superstructure as our first task description. This will be a summary task that will be used to group all the tasks associated with building the superstructure. The next task will be Pylon, with a duration of 7 days. It has no predecessor task, and we will click the Define Operations toolbar button to display the operations form. Select Add Structure for the operation and the group Pylon. We will use 0 days for the age at add since the material is steel. In addition to the structure being added, check the Include Object Self-Weight checkbox and load this group with a load equal to twice the dead load. On the schedule, notice that the columns have been populated with the operation, object, and details, including age, self-weight, and scale factor. Select the task and click the Increase Indent toolbar button to identify this task as a subtask of superstructure. Now we will add another task, this time for the first deck sequence, named Deck 1. It will have a duration of 3 days and will have a predecessor of Task 2, which means that it will not start until the completion of Task 2. This conditional relationship is shown in the Gantt chart. Double-click on the operation cell to bring up the operations form, and again we add structure, this time group Deck 1, with an age at add of 14 days. Self-weight is checked with a dead load scale factor of 2. We repeat this for Deck 2. Repeat this process until you have created tasks for all of the deck groups. Scrolling out, we can see how the tasks relate to one another on the Gantt chart. Next, we will add tasks after the construction to model the effects of time. We will input a task summary called Post Build, then a task called Time 1 with a duration of 3 days, a predecessor of task 22 but no operations. This task is only meant to mark the passage of time. No structure is added or loaded. However, we will specify an output label to ensure that we get output for this task, since it contains no operations and the end stage and end case checkboxes are not marked. Continue to add time tasks with the last task having a duration of 3,000 days. Older concrete is less sensitive to time and thus may have a longer duration step. It is important to realize that task duration can have a significant impact on creep calculations. Select the post-build task and click on the Decrease Indent button to identify this task as a summary task. Again, we can see the relationship between tasks, including summary tasks and subtasks. Before we leave the construction scheduler, we will select P delta from the Geometric Nonlinearity Parameters drop-down list to include P delta effects in the pylon and deck, and click the Modify Show button for nonlinear parameters. Make sure that the time-dependent material properties option is checked so that creep and shrinkage effects are included for the concrete material. We are now ready to leave the construction scheduler. As we exit, the scheduler generates the stages and load cases for the nonlinear static analysis. Clicking the Load Cases drop-down list, we see that a Schedule 1 zero load case has been created from the construction scheduler input. This load case is locked, meaning that no changes may be made to it using the Modify Load Case button. Changes can only be made in the scheduler. On occasion, however, we may want to make some changes directly to the load case, in which case we need to make a copy and then edit the copy. We will name our copy Bridge. And note that the stage construction load cases are a type of nonlinear static analysis. Also note that the P delta has been selected, as done on the scheduler. The construction scheduler typically creates two stages for each task: a duration stage with no operations and a zero duration task at the finish day where operations are carried out. Clicking on the Modify Show button for results saved, we want to make sure that there are an adequate number of steps assigned for the time-dependent items. We will use 5 for this model. Now we are ready to run the analysis. For this model, we will not run the dead, modal, or Schedule 1 cases, only the copied bridge case for the static nonlinear stage construction analysis. The analysis window is showing how the program steps through each stage. Once the analysis is complete, we can review the results. We will display the moment diagram in the deck for a particular step. For the step we selected, Step 60, the bridge is only partially complete. We can also create a video showing the segmental bridge construction along with the varying moments in the deck, which includes both construction and time effects. We will now switch to the undeformed shape. Next, we will display the longitudinal deflection of the deck at midspan versus time. We click the Define Plot Functions button and then select Add Joint Displacements. The point selected is joint 17, and we want the displacement in the X direction. We will limit the horizontal time axis to 300 days. Next, we will plot the axial force in 3 cables as it varies with time. This time we select the Add Frame Forces option and make sure that the axial force component is selected. We will plot the axial force in all 3 cables simultaneously against time. But this time we will limit the time axis to 45 days. It is easy to see the 3 distinct starting times for the 3 cables. Lastly, we will plot the moment midspan as it varies with time. This concludes this tutorial on stage construction.